So firstly, diode. Basically, it is an two-terminal electronic device. We can also call it as a semiconductor device. What is semiconductor? Basically, semiconductor is a device whose conductivity is in between insulator and conductor, wherein it offers very few conductivity. So this diode is built using those semiconductor devices. Basically, silicon and germanium are the material that are being used for making this diode, and we call it as a unipolar device because it passes current only in one direction based on the applied voltage. Basically, it has two biasing. One is forward bias and one is reverse bias. When you applied high voltage at anode comparatively to cathode, it is known as forward bias, wherein it allows the electrons and charge carriers, majority carriers, to flow across the junction formed, and it offers the very low resistance, practically in the order of cents. And ideally, we say it is 0 ohms, and it offers infinite resistance in other direction in the order of mega ohms. So based on the order, you might be knowing that doping and fabrication technologies. So based on the type of doping and amount of doping, we say moderate doping, heavy doping, and low doping. Like based on the intrinsic concentration, there are three different categories. If we are making it 1/10 of doping, means it is called as low level doping. And if we are making it equal and greater than intrinsic concentration, it is moderate doping. And if you are making huge amount of, like if you are adding huge amount of impurities, so it is called as high doping. So based on the level of doping, diode can be used as switches, rectifiers, voltage regulators, and there are different kind of diodes, namely Schottky diode, tunnel diode. So these kind of diodes can be prepared based on the type of doping and based on the bias you are applying, forward bias, reverse bias. We can make the same diode work in different kind of applications. Some of them are rectifier switches and voltage regulator. So we are going to see what a voltage regulator. How are we making this diode to work as voltage regulator? As you know, the second thing is PN junction diode. Before entering into Zener diode, I would like to tell about PN junction diode. So basically, what is PN junction diode? You might be knowing this, the basic thing, where silicon, carbon are the fourth group elements, where we use silicon as the main semiconductor in our present day-to-day market, because it is allowing, it has abundance of like we have abundance of silicon present in our earth. And the second thing is energy bandgap. It has a high energy bandgap. Because of that, it can hold high temperature atmospheric conditions, so that it cannot damage as easily as possible. And the second thing is, when we are using the extrinsic semiconductor like a p-type semiconductor and n-type semiconductor, after amount of temperature known as intrinsic temperature, the extrinsic semiconductor will behave as intrinsic semiconductor. It will directly convert into intrinsic. That is known as intrinsic temperature. The intrinsic temperature is the minimum temperature at which the extrinsic behavior of an semiconductor like an N-type or a P-type semiconductor will behave as intrinsic semiconductor. So that the intrinsic temperature is high for silicon. So that is why we are using silicon over germanium and other fourth group elements. Now, the N-type, coming to P-type semiconductor and the N-type semiconductor. N-type semiconductor is as usual, as we know that we are going to dope the fifth group pentavalent impurity elements like phosphorus, aluminum, gallium. These and all will be doping. So the four electrons from pentavalent impurity and four valence electrons of silicon will be bonded, and the remaining fifth electron of pentavalent impurity will behave as the free electron. So these free electrons uh, will be available for conduction and all. So that is called as N-type semiconductor. Whereas P-type semiconductor, we will be doping the trivalent impurities. So they will be, the three valence electrons will be bonded with trivalent impurity, and the remaining that vacancy is the hole, which is useful for the conduction of which is main reason for the flow of those vacant sites called as holes will be the reason for the current thing. So if we join those two semiconductor, N-type semiconductor and P-type semiconductor, there will be a depletion region formed. You can see here in the yellow region.
You can use the paint also.
Therein,
Whiteboard paint you can also use. There is.
So this is the yellow region you can see where we are going to mix P-type semiconductor and N-type semiconductor, and it will behave as the depletion region, wherein the electrons available and the holes available are moving apart, and it will behave as a like depletion region, wherein no electron or hole can't be. So this contact potential is called PN junction. In PN, as I told earlier, we are applying high potential at anode and low potential at cathode, it is according to our technical terms, it is known as forward biasing, as you know. So we will be applying that forward bias, and the majority carriers, majority carriers in N-type semiconductor are holes, and the majority carriers in P-type semiconductor are holes. So these will be moving from this, electrons will be moving from this region to this region. So they will be diffused based on the property of diffusion. As you might be knowing, diffusion is the transfer of electrons or holes or any particles from high concentration to low concentration. So this is called as diffusion. So based on the property of diffusion, we will be able to transfer the electrons from N region to P region. So this flow of electrons or this flow of holes is called as forward biasing. So based on the direction of flow, due to this flow of electrons and holes, we will be able to generate see the current passing through it. And in reverse bias, this depletion region will be becoming very high and high and high, but you can't be able to like the diffusion won't be happening. So that is why there exists high resistance, but practically there exist a few milli micro in silicon. You will be able to see microamperes of current in reverse bias, and in germanium you will be able to see nanoamperes of current. That is due to the minority carriers. Those will be traveling through that depletion region. In N region, holes is the minority carriers, and in P-type silicon, electrons is the minority carriers. So due to the transfer of these holes, like holes and electrons from N region and P region, the minority carriers, we will be able to see the microamperes and nanoamperes of current through the reverse bias. And coming to the Zener diode, basically to the diffused process, the basic construction is they say diffused process of N-type semiconductor and P-type semiconductor. And the main thing is it is highly doped. Like if, for example, if you say 10 power 14 electrons and 10 power 14 holes in intrinsic semiconductor, if you are able to dope the impurities in the range of 10 power 18, then it becomes the highly doped semiconductor, wherein the other terms is degenerate semiconductor, we can say. So because of this high doping, that working of diode is kind of new. What is that new thing? We are going to see a few seconds from now. So it is a highly doped PN junction diode, which is used as a voltage regulator only in the reverse direction. In forward bias, the characteristics of voltage, applied voltage versus the current which we are seeing will be the same. Like up to the cutoff voltage, what you say, basically the cutoff voltage is 0.7. So up to that voltage, no current will be seen. Beyond that 0.7 voltage, the current will be increasing exponentially in the forward bias. In the reverse bias also, up to some VZ, that is called base kind of the notation VZ, Zener voltage, up to that VZ, no current will be, the microamps of in silicon and nanoamperes in germanium will be, the current will be seen very few due to the minority carriers, as I said earlier. So due to this, we will be able to see the uh, current, few amperes of current in reverse bias. After VZ, like after the Zener voltage, Zener breakdown will happen. So due to which also there are two parameters we should be using. One is VZ, Zener voltage, and knee current. The minimum knee current should be flown through that Zener diode. Then only this diode will work as a voltage regulator. What is that voltage regulator? So you can see here in forward bias, the first quadrant, which you are able to see now. Here to some 0.7 volts, zero current will be there for a positive voltage. And after you can able to see the exponential increase in the current in order of milliamps for the applied positive voltage, forward bias voltage. In reverse bias voltage, you can see these are the microamps for silicon and nanoamps for germanium. And after that VZ, after the VZ, you are a sorry, after VZ voltage, like basically it would be around 5 volts to 8 volts. If you apply the reverse voltage of 5 volts, then what happens is the current will be rapidly increasing. The current will be rapidly increasing because those minority carriers will be transferring the tunneling effect, you can say. Because of the tunneling effect, the there will be a fast movement of those minority carriers. Due to this tunneling effect, what happens is uh, more number of current is generated, like more due to more easy and more number of flow of electrons and holes, those minority carriers, for a small increase in voltage itself, like around millivolts itself, huge amount of current will be lost due to huge amount of holes and electrons will be lost, due to which you can see the current, you can see the huge amount of current there. So that is why you can, this the technical term is multiplication factor comes into the picture, wherein that microamperes or nanoamperes of current is multiplied in some 10 power 6 or 10 power 3 times, wherein it becomes milliamps. So for the same voltage, they are able to see the huge amount of current passing through it. So the thing is that reverse bias of Zener diode will provide the kinetic energy to those electrons which are moving with the speed, and it increases with increase in the reverse voltage, which moves at high velocity. As I said earlier, due to the tunneling, they will be moving at high velocity. These high velocity electrons will collide with the other atoms available there. So these in turn will multiply, and create more number of free electrons. As I said earlier, 5 to 8 volts. It is the Zener voltage where we expect. The factors coming to the factors affecting Zener breakdown. If the depletion width is small, see, basically this is a general case. If the depletion width is small means, then you can jump here to there easy. No? So in the same way, electrons or holes can jump from one side to other side, due to which VZ can decrease. That means lower voltage of Zener voltage itself, you can able to see the breakdown. The breakdown means you can able to see the multiplication, like more number of electrons or holes that is passing. Band gap is small, then also tunneling it will increase, due to which Zener voltage will decrease. And the third thing is temperature. If you increase the temperature, means band gap will decrease. Band gap is there is a proportional between band gap and temperature in terms of power 3 by 2. So if temperature is increased and band gap will be decreased, due to which this Zener voltage will decrease. The Zener voltage decrease means that 5 volts, as I said earlier, it is the point where we see, but 5 volts will be reduced. Like you can able to see the more amount of a carriers pass it at 4 volts or 3 volts itself. So the basic chemistry behind this is due to the rupture of covalent bonds. If covalent bonds are breaking means you can able to see more number of electrons, free electrons, which are able to created at a high electric field. This basically occurs at low voltages. As I said earlier, it occurs at high volts. Basically, if depletion width is small or band gap is small, or if you increase the temperature, that 5 volts will may become 4 volts also. After breakdown, diode behaves as a voltage regulator. I'll show the circuit in next slide. What is that voltage regulator? And it happens in abrupt or step-graded PN junction. The meaning of this is here we are joining two semiconductors like p-type and n-type. What is the meaning of abrupt or step graded means? For example, if you take intrinsic semiconductor 10 power 14 electrons and holes. In p-type semiconductor, in p-type semiconductor, if doping is 10 power 17, and if in n-type the doping is 10 power 15, if we are mixing these two semiconductors, that 10 power 17 per centimeter cube and 10 power 15 per centimeter cube, then there is a where you can see the difference between 10 power 17 donor impurities and 10 power 15 acceptor impurities. There is 100 times difference. So if you join these two PN junction, then you can able to there this difference, the 100 times difference. If you can join, if you are creating Zener die using this P and N type semiconductor, then it is called as abrupt or step graded PN junction. And this is the basic circuit of voltage regulator, where we use Zener diode for that application of voltage regulator. Basically, we have series resistance, Zener diode, and load. So, what is the voltage regulator? Is we are see here you are applying voltage here. It is passing through RS and it is applied to VZ. You can able to see that positive voltage is applied at the reverse direction. Like in the negative cathode, you are applying at the cathode of Zener diode. You are applying high potential. That means it is reverse bias. So if you are applying, for example, let's say that Zener voltage is 5 volts. If you are applying a high voltage greater than this, then what is the thing happen is, so it experiences the reverse bias and it will provide the same 5 volts. See, the thing is, if you're, for example, let's say the load is lead and Zener diode is 5 volts. If you are applying, for example, by chance, if the voltage is applied is increased 5 volts to 8 volts, so then that time the LED won't get damaged because of the Zener diode. So the Zener diode you are using will provide the 5 volts of breakdown voltage, due to which the 8 volts or the higher voltage grade above the 10 volts, 12 volts, what you apply won't damage the LED. The same 5 volts of Zener diode will be applied to the LED and the load. So therein we are not damaging the LED by applying a high voltage. So this is the benefit of Zener diode, using it as a voltage regulator. The few things I would like to explain here, why we are using RS. The RS is to basically limit the current flow. This as I said earlier, there are two parameters to make Zener diode as voltage regulator. One is Zener voltage, and the second thing is knee current. So to balance those parameters, knee current and the maximum current, there should be minimum current, that is knee current, should be passed through this Zener diode that will make this Zener diode work as voltage regulator. So to make those conditions as a end user, like, to make it work, like to make it easier, like to make it in our hands, we are able to sorry, to make this Zener knee current, we are using this series to limit the current flow on it. And there is maximum current also. It should not go beyond it, or else this Zener diode can damage. So to limit those things and all, we are using the series resistance. And the Vout is the stabilized output. Like for example, if the breakdown voltage of that Zener diode is 5 volts, then that 5 volts is the stabilized voltage. If you are increasing your input voltage also, that 5 volts will be seen as the output.